multi-label zero-short learning with transfer-aware label embedding projection. Basically, the paper is about the zero-short learning approach for visual recognition. Basically, let's recap what the zero-short learning actually is. It's a technique to make predictions on the unseen data using the unseen labels, I guess, as well. So the paper mentions few of the things that well, this is a kind of the popular approaches that I used to somehow match the structure of the network predictions to the auxiliary structure that's used to get extra information from to actually be able to do any of this zero-short learning. So the popular approaches are as follows. It's the attribute description of the class labels, which usually requires manual annotation of pictures. Then there is a textual description from internet sources. You can use some natural language processing on top of that. The really popular one is word embedding, where you would use some pre-trained word embedding, like BLAB or Word2Vec, and try to map, try to use the structure of that embedding space to be able to make predictions from unseen labels. You could use some other stuff like co-occurrence statistics, which means like like web search co-occurrence statistics and different resources. And you could also use WordNet hierarchy information. Some previous work that mentioned in this paper is well, CONSE, LatEM, DMP, and FastTag. Those are some different approaches for doing zero-short learning. Yet, like first two are not really multi-label setup. They do modify them a little bit to do something like multi-label setup. I guess I just couldn't find many networks that are well, many approaches that are used to do the multi-label zero-short learning. It's not very popular. So let's briefly go over the ones that I mentioned. So the first one is convex combination of semantic embeddings. It's actually a really simple approach. Requires completely no extra training. You just take the you basically get the pre-trained network that is used for classification. Then you project those classification labels into the some word embedding space, any embedding space pretty much. And then you do the weighted sum of those embedded vectors. And after that, you do the search for like risk assigned similarity over all the possible, like all the labels you're interested in, I guess. You pick the ones that are closest one. So basically, there was another network called Device that is very similar to this, except the guys would actually train the explicit word representation, like the word embedding as an output of the first network. And then, well, the approach is exactly the same. So yeah, the way it works, you get the predictions from the network, you project those into the word embedding. Not project, you get the word embedding of the labels, I guess. You do the weighted sum by using the prediction probability as a weight, and then you normalize that by overall prediction probability that was that you used like for your label. So you would take like few labels that gave you the highest probability. You usually would not use all of the labels that you're using, and then you would sum the probability of those labels that were predicted to normalize this thing. But basically, they make a little bit of questionable assumptions. Like you could see that they say that they give this example of Liger and Tiger and Lion, which, to be honest, I don't think it kind of holds in any of the common word embedding. Like, I doubt it would hold in word2vecon and glove. Doesn't really make much sense, since, well, doesn't really make much sense. Well, surprisingly, they actually get better results than complete random, so it kind of works. Then there was this latent embedding network. Well, basically, the idea is you would get the features from this convolutional neural network, and then you would also take the embedding of the word, and then you would map those to the, like, both of those things to another space. But it will be like a linear mapping as well. But they would use like a lot of these different linear maps, and then they will pick just one linear map that gives the highest cosine similarity with like any class pretty much, and then they would use that as a prediction. So it's a little bit weird approach. So yeah, they do the, basically, sorry, I explained them correctly. So they take the features from the image, and then they take the word embedding, and then they use this matrix to first transfer the features from the image to this space, which is same dimension to the word embeddings, and then they do the dot product, and then they pick whatever gives them the highest similarity. Well, as a loss, they well, they also trained this thing a little bit weird. They would only train the one that gives the highest confidence for the class, and then basically they would train a lot of this kind of linear classifiers, very many of those, and then for the prediction they would use the one with the highest confidence, and to figure out the number of these matrices that they train, they either like do the cross validation with a lot of different like number of these matrices and then pick the best one, or they would train a lot of those and then just throw away the matrices that are not really getting used quite often. Then there was this direct multi-label zero-shot prediction. No, okay, so this one, it's very similar to the thing that first network was inspired by. Basically, it outputs the vector that's exactly the same size as the word embedding vector, and then it will do the cosine similarity across all the pretty much the power set of all the possible like labels you're interested in. So you would, like, at first you would actually oh no, sorry. So at first you would like you would first decide on which kind of labels you're interested in to do your zero-shot learning on. So you would define a set of those unseen labels in a way, and then you would calculate all the possible combinations of those labels by like just summing them, since they use word embeddings. They just add them up, and then you would use this pre-trained network to do the cosine similarity with those things, and you know, the highest result, that's one that they predict. Kind of easy and simple. Then there was this other network that actually had quite a nice idea. They would try to predict this principal direction for like given the image, and they also use the embedding word embeddings, obviously. So given the image, they would try to predict the axis inside this word embedding space, such that the labels that are present on the picture, they would be like they will have the highest cosine similarity pretty much, and the ones that do not, they will have the lowest cosine similarity. This is like so basically they did quite a lot of experiments, and it kind of holds the hypothesis that it is possible to find this this single direction. And then when they do prediction, they still go all over the possible labels, and then they pick some threshold of those. So this paper is a little bit different. Well, they do project both the image embedding and the word embedding into some shared space, where they later on would do some certain manipulations of the space, I guess. So the idea is that, well, first of all, they add some auxiliary label, which is like some unexisted label, and they train that along with the network as well. So they would first, yeah, so basically the intuition behind this paper is kind of as following. That they claim if they oh, sorry, 1 second. Yeah, exactly, this is the thing. So they claim if they decrease the distance between not the distance, if they increase the similarity between unseen classes and seen classes, and then if they also decrease the similarity between the seen classes, that would make this transfer learning, not the transfer learning, zero-shot learning problem easier, which is a somewhat questionable thing. When, well, as far as I understand, they kind of take most of the space this way, so they will like spread their scene labels kind of evenly across the space. That will make this the part of the loss that is responsible for well, increasing for decreasing the similarity of the scene classes highest, and then they would kind of, well, I'm not very sure how to visualize having the unseen classes being most similar to the seen classes after the first unfold. But somehow I think that would make it take most of the space. So during the training, they basically have some margin of the confidence. So they would calculate the confidence on all the labels that this images classifies into, and then they would pick the one with the smallest confidence. They would use that as a minimum thing, minimum value. They would try to have at least, well, they will try to have certain margin between this and the auxiliary class, and then they will also pick the class from the incorrect labels that has the highest probability, and they would also try to make that smaller confidence than this auxiliary class. So yeah, they make quite a lot of not exactly assumptions. Well, they impose a lot of conditions on this, the way they train this. So the U matrix is a matrix that transforms the word vectors into this auxiliary space. So they do want to have that orthogonal. So because some other laws that they have is well. So here, if the matrix is orthogonal, they take this word for all the words that I think don't belong to the correct class. They take the word and then they push it into this auxiliary space, then they take that thing back, and then they try to calculate the cosine similarity with the correct label. And then they want that to be less than the, sorry, well, oh, I don't, so this is for incorrect part of the label. So it's the sum of all cosine similarities between the incorrect labels and whatever was predicted. And this is the same thing for the correct version, I guess. So they also add a bunch of extra information. Well, the way I kind of skip through a lot of math because, well, first of all, I don't understand it too well, and then second of all, I would prefer to spare you from that. Basically, they reformulate this loss like this and the combination that they had before. Oh, also the regularity weights, obviously. So they reformulate that as like trace of, well, I'm just going to show you. So yeah, they reformulate it as this. So the Q will be the factor that's responsible for normalization. When it's reformulated like that, they can later on add this extra. Well, they would calculate this extra information from the auxiliary sources. Like for the word net, it will be the distance between the word and the other labels, I guess. And for co-occurrence statistics will be like the amount of the time words occur together versus amount of the time they occur by itself. And then they would, using this matrix of like all the possible combinations of labels, they would make a Lagrangian out of it, and Laplacian, my bad. And then they would use Lagrange multipliers with all this. Well, the reason for Lagrange multipliers is not exactly clear to me. I assume that's because of the bunch of constraints they impose by having this matrix orthogonal. Also, I have not really worked with this particular Lagrange multipliers thing. Well, pretty much that's where I'm at as well. I have not got much further into this. Basically, I skimmed through it, but like I wouldn't be able to actually explain you much more than that. They kind of prove that this regularization term works for them, as in like they decrease it and the results decrease as well. They also explain how they do the training with this setup, because they are not able to train it in one step. They do like at one iteration, they train this Lagrangian multiplier that they like using this decomposed laws. And then once and they claim that they can be directly solved, which I'm not very sure how to do. And then they also train this orthogonal matrix in the second step, and they kind of iterate those steps. Yeah. Here are some results with some metrics that I also didn't get to explore. MIAP is well, I'm sorry guys, I think it will be better off if you're really interested, you should just look at this out. I'm also not sure what Nizam microfan or macrofan, no, Hamiltonian score is. Hamiltonian loss, Hamming loss.